Hello, welcome to another session of El Zoominario. Today we are very happy to have Brenda Betancourt, who was born and raised in Bogota, Colombia. After that, she obtained her PhD in statistics at the University of California, Santa Cruz, and she is currently a senior statistician at a nonprofit organization called NORC at the University of Chicago. But now I've just learned that she's actually in DC. So welcome, Brenda. Thank you very much for taking the time to be with us and to tell us about your research. So please take it away.
Thank you so much, Daniel, for the introduction and for the invitation. So today I'm just going to be giving an introduction to record linkage to a very high level first, just so to understand the problem. And then at the end, I'm going to touch a little bit more on what my research has been on this area. So what is record linkage? Record linkage is the integration of multiple data sources of information with the idea of removing duplicated information, right? So we might have these days with the big data boom, we have a bunch of sources of information, and in many cases, we might want to merge them. So we have additional information to maybe later perform some statistical analysis or any kind of analysis. So the idea here is that we're going to have duplicated records in some cases, but the difficulty is that the records might be corrupted or noisy in the sense that we might have, say, different spellings of names, typographical errors when the data was input, out-of-date information. For example, if we're thinking about people, we might have two people or one person that has its name, and then maybe we have two different addresses for that person, right? Maybe this person moved, and now we have out-of-date information. I mean, we might not know what is the most recent one, right? Or it can also happen that this record is actually two different people that just happen to have the same name, but they live in different cities, right? So, of course, the process of record linkage and in general, just merging information is particularly challenging when we don't have any unique identifiers across the different databases, right? So, of course, if we have, say, a social security number for all the databases that we're trying to merge, that should be a pretty easy process, right? Because it's only matched by social security number, and that's a very clear unique identifier, right? But in a lot of cases, we don't have that information across all the databases, and we might also have cases where we're dealing with anonymized data just because it's sensitive data. Just think about health data. They might not want to tell us people's addresses or other sensitive information necessarily, or we might have the sensitive information, maybe diseases about them, if that's the type of information we're interested in, but we don't have clear, unique identifiers because they don't want to disclose who this person is, right? Just because it's sensitive. So those cases are the ones that are harder, but I'm going to touch on some of the basic ideas of record linkage, just how it's dealt in practice in simpler cases, and then go to, I guess, the more advanced methods. That is where I've been working on more. So record linkage, the general idea is try to identify records that correspond to the same entity. In this example, again, I'm just talking about people, but it might not be people. Maybe you have records about institutions or companies, citations in journals, any kind of information you may have. If you have a bunch of databases with that information, you might want to try to merge that just to have a more complete data set, right? But again, here I'm just showing an example where I have, assuming that I have three databases, one from Amazon, one from Google, one from Apple, and I have some people here. I just have the names here. Generally, when we're trying to do record linkage, we need more than just the names, right? That would be too little information to try to do a record linkage process, right? Think that we might have their age, their zip code, their phone number, that type of information. So we see here that we have someone, her name is Becca Stewarts, right? And then in the Google data set, we have the RC Stewarts, and then in the Apple data set, we have her as Rebecca Stewarts, right? So here I'm assuming, I know this, because it's a toy example, that this person, Rebecca Stewarts, and RC Stewarts, and Becca Stewarts is actually the same person, right? So as you see, something as simple as having a different spelling or nicknames or things like that of a name is going to make the process of record linkage harder when we don't have unique identifiers, okay? So same here, right? Another example, Jerome and Jerry, same person, and David Donson, same person, again, different spellings. So this is the type of problem that we're trying to deal with in the context of record linkage. So some areas of application for record linkage are, for example, human rights. One example of this is death counts estimations in the Syrian war. So there were 4 human rights organizations in Syria collecting data on deaths, so that this would be just people coming to them saying, oh, this person with this name passed away in the bombing that occurred in this specific town, this specific day, for example. So in some cases, people were reported more than once, and to be able to estimate the actual death count in the war, which is, of course, a very important quantity here, they had to do record linkage for that. Okay, so there is, if anyone's interested in reading about that, there's kind of fancy methods for that. There is a paper, but that's just a case where clearly doing the duplication, right, and identifying unique records of the people that died is a very important process, right? Another example of that is also detecting killings that were reported to multiple times to the United Nations Truth Commission for El Salvador. Again, these are homicides registries. They have different sources of that, and they were, again, trying to estimate the number of deaths that happened there, okay? So that's just an area of application in human rights. There are also areas of application in small area estimation or general population statistics. So, for example, we might want to estimate a demographic quantity or an indicator of interest in particular for periods that are intercensal periods. So this happens a lot in Latin America, for example, where we have our censuses are not like super even out or every 4 years, or right, like we have, at least in Colombia, sometimes we have them every 10 years and then, right? So there are quantities of interest that we want to know in between those 10 years between the censuses, and we want to do a small area estimation, for example. Small area estimation is trying to estimate at levels that are lower, say, here in the US than states, for example, right? That's a big area. We might want to have some estimates at the county level or some quantity of interest, right? So to be able to do that, a lot of people are just using multiple administrative record sources to kind of like feed and inform those demographic quantities of interest, right, to do the estimation of that. And in this paper, they did have some health system information, some databases for the armed conflict. This was based on data from Colombia, and some data from the educational system in Colombia. So you can think, right, all these sources are, again, going to have a bunch of records of people. They don't have unique identifiers, right? Kind of like a social security number. They don't necessarily have that. They will have some, hopefully, decent identifying information that you can use then to try to merge that data and then have an integrated data set to then do the population projections, for example, or the estimation of some demographic indicators, okay? And then a big area of application, which is one that I've noticed or that I've been working more since I've started my work at NORC, is just public health or precision medicine in general. So there has been a big investment from the government, right, to reduce costs and administrative burdens by using electronic health records or electronic medical records. So there was a big shift from, you know, having all these records on paper, which was obviously not very efficient, to having them in a digital format. And so this obviously is a very, again, clear way of using record linkage, where we might have data from hospitals, other electronic records, pharmacies, employers, labs, right? And we might have a bunch of information there that we want to merge. And again, we might have issues of this data being maybe anonymized because it's sensitive data. So the problem of record linkages becomes more difficult. So one key concept, this is in general for statistics, not just for record linkage, but there is also a big push these days on being on data confidentiality, right? Which is just basically balancing the risk between data disclosure and utility, right? In the case of healthcare, for example, they don't want to disclose that much, but also data utility, because we are doing record linkage to get all the information that we can. And a lot of these more complete data sets are used then to do statistical analysis that then lead to policy making, for example, right? So it's a balance between that, but again, it's just one more maybe roadblock or issue that we might have sometimes because we don't have accessibility to, again, all those unique identifiers that will make our life easier when we're merging databases. So in general, just for, you know, the basics of record linkage, we're going to want to have our data standardized in an homogeneous way, right? So we want to transform any variables that we're going to use for the linkage into the same format. If we have different sources of information, obviously doing things as putting dates in the same formats. Let's say if we're comparing names, just do the basics and transform all your names to capital letters, right? Those are basic things. Generally, what we do is to parse the information into pieces. So if we have a date of birth, then we will use the month, the day, and the year of birth as 3 different fields of information to do the linkage process. And then another thing to take into account is to avoid introducing redundant matching information. So if you have a zip code, which is more specific than the county of where the person lives, then you should first at least use the zip code to try to do the match, okay? So just basic standardization. And the simplest way of doing linkage is, of course, deterministic linkage, which is just best when we have high quality data, right? Again, this is the simplest case. Your databases are super clean, minimal errors, no typographical errors, updated information, right? You can just go and do deterministic linkage, which means you're just going to have or compare every pair of records, and each pair is going to be considered a match if the records agree exactly on the values of all fields that are used in the linkage process, right? So again, if you're just using data, different data sets, standardize them, so you don't have this issue of having capitalized letters with lowercase, but it's the names should, in this case, for example, will match if you just standardize them. And deterministic linkage can be done in this way, right? Just by comparing, let's say you have the birth dates. So if they match and their names match and their zip code matches, obviously that's a very easy way to do the linkage, right? So the deterministic linkage can be performed either in a single step, which is very uncommon, or using an iterative strategy where you can, for example, first match on zip code, and then for exact matches on that, you can, you can get exact matches from that. And if you have maybe don't have the information for the zip code, or it might be noisy, then you can use the county level information or the county information for the people to do a second pass to see if some of the people that didn't have the zip code first can be matched. So it's relatively simple when you're doing deterministic linkage. Of course, one complication just by doing a simple process like this is still like if you're dealing with millions of records, then it's still kind of like cumbersome, but it's relatively easy now because you can break it down into smaller problems. Of course, that's the simple case, but again, remember that in practice, we do have noisy information, right? So instead of just matching exactly, right, because that if we have a misspelling of a name, then that exact match is not going to work. We do approximate, or we use approximate string matching. And some of the similarity metrics that we use are, these are the most famous ones, are Levenstein and Jarrow-Winkler, which basically give you a number back telling you how similar, say, two names are. So for example, Adam and Alan, they have a Levenstein distance of 0.5, or similarity. In this case, I'm talking about similarity. And here again, Adam and Alan, if we use the Jarrow-Winkler similarity measure, they are, they give you, this similarity metric gives you a 0.7, right? So now, right, you have kind of like an approximate or like a similarity, sorry about that, a similarity quantity there that can help you, but it's going to help us to then decide if those records are the same for the same person or not. Then, as I was mentioning, one of the challenges in general, just even with the basic linkage, is computation, right? So if you perform all pair comparisons between two files, say one is of size 100 and the other one is of size 1,000, then you're going to have 100,000 possible comparisons, right? And these are just very small size data sets. So one strategy that we use in general is blocking that helps you reduce the comparison space to record pairs that just have certain commonality based on one criteria. So I'm giving you here just a simple example. Let's say that I'm only going to compare records of people that share the same last name initial, okay? So if you have all these data points here and you were to compare them all, you can reduce that comparison space by only performing comparisons of people with the last name that starts with R, only with J, and so on. And that is going to reduce your comparison space a ton. And of course, computationally, you can run these processes in parallel, right? You can just find your matches here, here, here. And so it can break the problem into many pieces, which is quite helpful when you're doing linkage for big data scenarios, right? Okay, so that's kind of like the basic deterministic linkage. And what I work more on is actually probabilistic record linkage, right? Because again, data is never that clean, right? It's not doing it in a deterministic way, is not gonna give you the best results. So one of the most famous probabilistic record linkage methods is called the Fellegi-Sunter approach. And this is just for the simplest case where you're trying to link two data files and there are no, one of the main assumptions is that you have no duplicates within the data files, but of course, you're trying to look for duplicates across the data files. So how this works, just very high level, is this represents, you're going to represent every pair of records using vectors of features that describe the similarity between individual record fields. So again, how do you get those similarity? If you have names, then you use some of those distances or similarity metrics that I just described. You're going to place feature vectors for record pairs into three classes. They're going to be classified as matches, non-matches, and possible matches. And then you're going to perform a record pair classification by calculating a likelihood ratio of those probabilities of matches and non-matches for each candidate record pair. And then based on a threshold, you're going to choose two thresholds. You can kind of like separate your data, say, okay, The record pairs that are above this probability, I'm going to say they're matches or possible matches. These are non-matches, and then in the middle, there might be some gray area where you're like, okay, these are possible matches, but I'm not sure. So this is how very high level the probabilistic record linkage method works, right? So now, again, one of the issues is that there has to be some human input for this to work, right? Someone has to choose the thresholds, that's okay. But then you still have to do a post-processing step where you're looking at the possible matches and trying to discern if those are the same people or not. So another limitation is that, well, besides the fact that it's only for 2 databases, is that we don't have transitivity when we're doing this type of analysis. So we have 3 records here. The records A and B are declared to be a match because they have the same names, the same phone number. But it happened, say that in our process, records A and C are declared a non-match. Okay, so Mary Smith, this one, and this one are not a match just because they only agree on name. They don't agree on address. We don't have a phone number, right? But if you see B and C, those are also declared as a match, right? Because they share the same address. So by transitivity, you would expect that A and C will also be declared a match, right? But that doesn't happen with this type of method. So that's why it requires some human input, and it kind of makes it harder. But still is one of the most used processes. We still use it at NORC, for example, with some improvements, but it's still one of the big methods for record linkage. Okay, so if you're interested in this type of method or playing a little bit more with cleaning data, using metrics to compare strings, you can go check out the record linkage package in R for the people that use R. I'm sure there is an equivalent of that in other programming languages, Python, right, or any other software that you can think of. So these limitations that I just talked about, first, that is only for 2 databases with, again, the assumption that there are no duplicates within, and the fact that we don't have transitivity is the motivation of the work that I've been doing since I actually, during my postdoc, you didn't mention that, but I did my postdoc at Duke, and over there, I started working on this idea of addressing record linkage as a clustering problem. So if you think about record linkage again, where we have, again, say 3 databases, and we're trying to identify the people that, or the records that belong to the same person, then you can think of it as clustering these, for example, here, these 4 records, right? Putting them in the same group because they represent the same latent entity, which is this one unique person that I want to find, right? So you can do that process. You could just address this as a clustering problem where you just put records that belong to the same person into the same cluster, okay? So for that, what I've been focusing on, my specialty is Bayesian statistics. One of the big ways of doing clustering, not just for record linkage, but in general, is using partition-based Bayesian clustering models, okay? And in practice, many clustering tasks are going to require that your cluster sizes grow linearly with the size of the data set. What does that mean? It means that in many problems, you really just want to have a few clusters with a bunch of elements in it, right? Whatever the clustering is, let's say people, if that's what we're doing. So one of the main models that are used in Bayesian approaches for clustering, this is specifically Bayesian non-parametrics, is Dirichlet process mixture, which has this Chinese restaurant process representation, which is very self-explanatory. This is just a probability distribution for random partitions, okay? That is this Dirichlet process with a parameter alpha, where alpha represents the probability of opening a new cluster, basically. So when you're getting this Chinese restaurant representation means that you have, I don't know why it's a Chinese restaurant in particular, but you have a Chinese restaurant and each cluster is basically tables, right? And you have a customer that comes in, then you're gonna seat that customer in an open table with probability proportional to the number of people that are there, right? Here I have 5 people, so this cluster will have a higher probability of have someone else sitting there according to this criteria. Or you're gonna seat that customer in a new table that you just open with probability alpha. So this creates a natural partition of your data. And this Bayesian non-parametric process, what it does, the advantage that it has compared to other clustering approaches that are not in the Bayesian realm, is that the number of clusters is actually estimated from the data. You don't have to give it to your model in advance, which happens a lot with any other machine learning algorithms. Generally, you have to choose how many clusters you want, and then it gives you the clusters. Here, you just give it the data, and it gives you everything back. It estimates it for you. So under this same idea of basically partition-based Bayesian models, that's where my area of research has been focused on. I'm not going to talk about it in detail because it's kind of mathematically heavy, but I hope you at least understand what the main problem is and why it's hard, right? Why record linkage is hard. So my focus is on microclustering models. So as I was mentioning, in most applications for clustering, you just want to have a bunch of, few amount of bigger clusters, right? That gives you groups. Here for record linkage, that's not the case, right? You can think that if you're merging 3 databases, let's say that you don't expect duplicates within, then you might expect one person to just show up 3 times. Right? So you don't want to have a cluster of size 100 because that would mean that a person showed up 100 times, right? That doesn't make sense for this context. So we came up with this idea of microclustering, which means simply that each cluster should be or remain small even as the size of the data increases, okay? And other applications, we just propose basically probability distributions or random partitions, right? That same idea of the leadership process that are gonna help you do microclustering, right? When you want smaller clusters. Other applications for that beyond record linkage are just clustering of DNA sequencing, analysis of sparse networks. You could use the models that we propose in other contexts, but for record linkage specifically, we actually have a NAR package, if anyone's interested in looking at that. The package is called Microcluster, like this, spelled like this, and it does record linkage with categorical variables only. That is for cases where you have anonymized data and all you have is categorical information. And that package uses the microclustering models that we propose. If anyone's interested in the math, you can look at the paper that was published recently, but I just hope that the main description that I gave you just gave you an idea of what the record linkage problem is. Here are some references of some of the applications that I show you. And yeah, so that's kind of like my job talk part of the presentation. And now I am going to talk a little bit about the region where my family is in Colombia. So I was born and raised in Bogota, but all my family is from this department in Colombia that is called Tolima. Tolima is one of the 32 departments in Colombia and is located in the Andean region of the country. So it's this part here. And where my home is now, because my mom just moved back to there, right? Every time I go home, basically going home back here. So this is actually a picture of the town that is called Valle de San Juan. This is where my mom's house is. And this is actually a picture that my brother took So this little house that you see there is one of our neighbors. It's just absolutely beautiful to be there. And the nicest part is that there is no internet. So it is always a retreat when I go home. So Tolima is a very culturally rich region, I guess, as any part of Colombia, really. And one of the traditional foods that we have is called tamal, I guess, kind of like the Mexican tamales, but they're very different. So this is what a tamal looks like. It is cooked in a plantain leaf. That's what you see out there. And then the inside is basically kind of like a corn mash, and it also has pork, chicken. Some of them have rice and maybe some chickpeas or things like that. And here you also have the arepas, even though I didn't put the name in there. That's kind of like more a general Colombian thing. And this is generally a breakfast type of meal. That's why you have it kind of like with hot chocolate, and is one of the most traditional foods in the Tolima region. And then over here, I'm showing you a picture of a folk dance that we have. Is the most traditional, yeah, it's one of the traditional dances of the region that is called El San Juanero. And it's very beautiful. These are the traditional way, this is the traditional way people dress to dance. There is always a hat involved and a scarf, and it's still preserved, I guess. I really appreciate that still kids learn how to dance these traditional dances everywhere in Colombia, but the Tolima culture is particularly beautiful. Okay, so that's all I had. Thank you so much.
Thank you so much, Brenda. This was really nice. And now I'm going to stop the recording. So,
okay.
And then we can take some questions offline. Okay?
Okay.